All right, we're going to go ahead and kick things off here. Today is the first half of a two-part series where we break up reverse engineering into two different types of geometry. The prismatic and mechanical geometry, like you're going to find on your garden variety machine part, and organic or freeform geometry, like you'd find on an ergonomic grip or on the human body. So today we tackle a little of both, but mainly we'll focus on that first category today. And on the 23rd next month, we'll do a deep dive into working with those organic shapes. We have Sean Parker and Matt Fisher with us today. They're both mechanical engineers who specialize in 3D scanning applications, and they're going to demonstrate the workflow and show us some examples of how to use the tools at our disposal to approach these different types of geometry. Before we dive into the actual modeling, I want to take a minute to address a couple idiosyncrasies of the 3D scanning world that can cause some confusion if you aren't aware of them. And the first one is what we call arbitrary units. So in the CAD world, we're used to the CAD file having specific units which are chosen from the beginning. But mesh files evolved a little separately from CAD, and they use arbitrary units, which is to say they don't store a unit type. They store the number of units, but not the type. So a scan file knows that it is, say, 324 units long, 324 of something. But it has no idea if those units are inches, millimeters, or whatever. No, you're not the only one who thinks that's weird. We think so too, but it is what it is, and it's a common source of confusion in reverse engineering. You want to be aware of it when collaborating with others and communicate the correct units. So to that end, some programs will prompt for a unit type when importing a mesh file, like this one here. Others may prompt selectively if the part appears really big or really small. It'll be like, are you sure this is right? And in general, CADs will have a unit selection dedicated to mesh files that's separate from your CAD workspace. So you can import a mesh in millimeters, but still be working in, say, inches in your CAD workspace. In SolidWorks, here it doesn't prompt automatically, but if we select a mesh file type from the file type dropdown, we'll see this dedicated options box. It's dedicated to that file type, and of course it includes units. So we'll select the same units as our scanner output. Something to be aware of. One thing I like to do when working with others is I like to put the units in my file name. So I'll name it something like, water pump underscore V2 underscore inches or something like that. And that way everyone knows what they should open it up as. Another thing to be aware of is what we mean by design intent. I realize a lot of you are SolidWorks users, and if you've taken a SolidWorks Essentials class or learned it in school, this is one of the first concepts you hear. They're basically referring to the practice of thinking ahead, just like you would in a chess game, and thinking about how the moves you make now are going to affect what you're able to do later on and how you do it. So parametric CAD models consist of a bunch of interdependent features stacked on top of each other. So you need to approach the modeling in a deliberate, thought-out way that's going to result in the model being highly stable and highly editable downstream. But that's not what we're talking about when we use the term design intent in reverse engineering. And to be clear, that type of thinking ahead does come into play in reverse engineering because we are creating CAD models and we're using fairly traditional CAD commands to do it. But in reverse engineering, we use the term design intent or designer intent in a much more literal way. And we just mean what the designer intended and what function the part was intended to serve, as opposed to what came out the other end of the manufacturing line, which is going to be imperfect and differ from the CAD file in several ways. So, if there's a sunken area on a cast part, or some little nub where the gating was cut off, or warping in a molded part, or this part here, the flanges are at kind of odd angles and nothing really lines up. And those are all realities that the designer didn't intend, and we wouldn't want to reproduce them in our part. So instead, we can break the cycle here and now. We can correct them or ignore them during the reverse engineering process. And that's in contrast to an as-built model. If you need to connect two pipes on opposite sides of this factory floor, doesn't really matter what the designer or where the designer intended those flanges to end up. All that matters is where they actually ended up. And if we want to connect them, we need to work off the imperfect reality. Doesn't matter where the blueprint says they should be. So that's what we mean by design intent. We're just referring to what the designer intended. It's not ideal that this term is used in such different ways, but again, this is the kind of thing that happens when two disciplines evolve apart from each other and meet in the middle. So hopefully you won't be confused when we use this term today. And with that out of the way, let's dive right in. I'll turn it over to Sean Parker with 3D Systems, and he's going to show us what your average reverse engineering process looks like.
Awesome. Thanks a lot, Ian. Just a quick plug for what we're going to be taking a look at today. Software-wise is our product called Geomagic Design X. This is our flagship reverse engineering software for converting either point clouds or more commonly 3D scanned mesh objects into a history-based CAD model that's compatible not only as just a dumb solid, IGES or STEP or Parasolid export with things like SolidWorks and other CAD systems downstream, but also can generate native files. And what I mean by that is transferring all of the design history, the sketches, the reference geometry, modeling operations, all of your design history out of Design X and rebuild it inside of software like SolidWorks, where you can make edits to it there. The process that we're going to use on this little part is going to be basically like this. We're going to import a file from an external source in the STL file format. We're going to check our units and make sure that they come in the appropriate units, as Ian was alluding to before. We're going to kind of recognize some of the features on that model and then start to use those features to generate some sketches, standard design procedure. And then from those sketches, we can start to use them to make features and add details like fillets and some of the other holes in this thing. And at the end of the demonstration here, we'll go ahead and kick this model out into SolidWorks and interact with it a little bit there. So getting out of the very brief slideshow that I had here, you should be able to see my screen with Geomagic Design X on it. And even without any data in it, there's going to be some familiarities here for those of you that are used to using Creo or NX or SolidWorks, where we've got a history tree on the left-hand side. We've got a tab-based tool palette up above. The software is actually very simple to pick up and learn, especially if you already have a history-based modeling experience. So what I'm going to do is I'm going to import some scan data here. I'm going to grab it from this folder. And this is a mold insert. Now, again, I don't know the units that this object was scanned and exported as, but I do have a little bit of a scale bar down here that's kind of give me a decent representation of what this part is size-wise as it exists in the CAD system. And if I want to do a little bit more detail level stuff, I can see that it's about 70 by 65 by 45 millimeters. And I happen to know that those are the correct dimensions for this mold insert, but there are some tools where I can override the units and make sure that this part is represented properly size-wise when it's in the software. Now, the first thing that I recognize is that, I've got my default views kind of oriented to the screen here, and the part shares no real orientation to those standard views in my X, Y, and Z axes, my front, top, and right plane. So what I want to do is I want to transfer this model from its as scanned position to something that's a little bit more useful when I'm going through the design process. And that's usually going to be referencing some of the prismatic planar features on this part. Now, Design X does have a full 3D scan data modeling or management tool set in it, where I can make selections very similar to Photoshop or MS Paint or something like that, and best fit geometries that way. But we do have a little bit more of a interesting tool set in the auto segment and region grouping functionality. Basically, what this does is it lets the software automatically recognize areas of common curvature on my scan data, and it kind of picks apart the model and it represents different regions as different colors and allows me to interact with the model in a little bit more natural of a way for those of you that are used to working in a CAD design system. So running the auto segment tool here allows me to adjust the sensitivity that I want to run this at, basically how much curvature I'm going to need to separate a given area of the scan data into multiple regions. And I'll leave it at a small fraction, 24% here, and let it run. So it's going to kind of disassemble the model, essentially finding all of the component geometries on it. It's going to assign a color to those geometries that makes it a little bit easier for me to view the model and interact with it. It's also going to recognize what type of geometric entity that certain region is. And so that's the step that it's on right now. It's actually classifying all of the regions as either planar, cylindrical, conical, spherical, toroidal, freeform, or revolution shaped. And so once I hover my cursor over some of these regions in just a second here, we'll see that represented. So I've got planes, I've got cones where I have a chamfer here, I've got freeform shapes where I've got organic shaped areas, I've got revolution, cylinders, toroid, so on and so forth. I've also got some ugly stuff here, and I've never really made any changes to the model yet. I've just kind of broken it apart to make it a little bit easier for me to work with. If I do a little bit more digging, I can see that there's a lot of issue with some of the areas on this scan data. So this is kind of to Ian's point from a second ago, where things like these dents, things like this area here where maybe there's a little bit of clay or something like that, maybe some paint that wasn't scraped off, and areas like this that appear to be scratches, they don't really need to be represented in the final model. When I'm rebuilding this, and especially if I'm going to be cutting a new one of these mold inserts out of billet, I don't want any of this stuff to show up in the final model. So my design knowledge can override what the scan data tells me that the part looks like. So let's go ahead and kind of get working here. And first things first, let's move this object from its current position to a location that's a little bit more useful for me as I'm going through the modeling process. Now, we do have some automated tools that can help us with that on the alignment tab here. The Align Wizard tool can recognize areas that have, generally speaking, it's going to look for things that have like a cylindrical or some sort of revolve profile that intersects a planar region on that. And it does that very nicely for us, except for it puts our origin way out here, which is the center point of this cylinder right here. And that's not particularly useful for me. If I was designing this from this, ground up or from scratch, I'd probably throw my origin maybe in one of these corners here. Now, I do know that this is a strangely shaped part. I don't have 3 perfectly orthogonal planes here, but I can kind of, get rid of the automated alignment tool and just work with this using my own knowledge a little bit better. So I'm going to select plane down here as my base plane. I know that this large plane here is pretty close to orthogonal to it, so I'll select that as my secondary datum. And if I've got a place on one of these corners maybe that I want to use as my third datum, or if I want to just kind of sit it somewhere towards the middle, I can either choose to lock down that degree of freedom or keep it open. And in this case, just for the sake of spending as little time doing this as possible, I'll go ahead and accept the orientation of this scan there. So now when I use my standard views, you can see that this part has been oriented to the origin very easily, very quickly, and we can go ahead and start to model. At this point, we need to put on our CAD engineer hat and visually look at how this part was designed in the first place. I can see a feature here, 1, 2, 3, and 4 planes, maybe this guy as well, that essentially tell me that there's an extruded shape there, and that's going to be extruded in a, at least in this area here, in a non-normal direction to my standard planes here, and that's fine. And I've also got what appears to be a series of cylinders or revolved shapes here that share a common axis with a couple of guys over here. This is going to be the main feature of the part. And so what I'm going to do is I'm going to work on building this larger feature first. I'll add this guy next, and then we'll remove some of this more organic stuff on the top here. I'm going to go ahead and create what we call a mesh sketch on this bottom plane here. And a mesh sketch is really just a cross-section of the scan data that's then projected back down onto the cross-section plane that I chose. So as I move, and especially if I hide my scan data, it makes it a little bit easier to understand what this is doing. As I offset this cross-section, I start to pick up different geometries on the scan data until I've passed all the way through the scan data. Now, this isn't going to be particularly useful to me because as I get up into the features that I actually want to take a cross section from, which is some of these regions up here, I'm still operating parallel to this plane, and I'm not taking into account the fact that the ultimate goal here is to create a revolved shape. So I can switch my method for my cross-section setup from a planar method to a rotational method. So instead of doing a linear offset from that base plane, I can do a rotational offset. I just need to choose where my central axis is. My central axis is going to be the axis of one of these cylinders over here. And now instead of offsetting away from it, I'm actually rotating around that center point. So this whole body, though, that I'm trying to create minus this first extruded shape here is not easy to sketch if I'm only taking one cross-section of it. If I'm taking a cross-section up here, I'm getting all of the top of this feature, but I also want some of this stuff down below and on this area down below as well. So what we can do inside of DesignX is stack cross-sections. And what I mean by that is by adding a section here and taking that section down into a place where I'm picking up more geometry. And you can see if I hide everything here, the blue dotted line is basically going to be the composite cross-section that I get by stacking both of those on top of one another. I can also shrink my cross-section in, so I'm not picking up some of the geometries that I don't want to measure right now or want to cross-section, for example, this extruded feature, which I'll get to in a subsequent step. So essentially just trying to isolate the areas of the scan data that I do want to sketch here. And when I go into that sketch mode and hide my scan data, I get a cross-section that's almost complete of the first feature that I want to build and do a revolution from. Now, when I'm in my sketching tab here, most of these tools are going to be extremely familiar to everybody that's done mechanical design inside of a history-based CAD package before, so standard CAD Sketcher. The one tool that's an exception to that rule is called Auto Sketch here. Now, obviously I have a pink cross-sectional guide on the screen. We call these polylines. They're not a sketch though, and that's a good thing because I've taken two cross-sections in two different areas of the scan, and I don't want to sketch this center part here because that's not going to actually be useful in this revolve. So I can choose to ignore areas of this and only sketch the areas that I want. So the Auto Sketch tool allows me to convert certain polyline entities into sketch entities that can be used in the modeling operation later on down the line. When I open up the Auto Sketch command, anything that the software recognizes on that polyline that is linear is going to be represented by a green color. Anything that's going to be a three-point arc or a circle is going to be represented by a yellow color. And so fitting lines and arcs to this cross-section is extremely easy to do. All I have to do is click the area where I want to place a CAD entity, and the software will do that for me. Now, there's a couple areas here that I want to take a little bit more manual control over, though. So once I place all of these entities where I need them to be, I can go ahead and exit this command and take a little bit more manual control over here. And that's because I've got some very small, very niche geometry that I want to be able to control a little bit easier. So if I open up the line command, I can just best fit lines to small sections of that. In this area here, I can drag my cursor over a section of the line and build a line there. And then just double click to add the last couple of features. Now, this guy that I just built here, this guy actually should be a composite of these two lines. So I can kind of best fit one line to these two sections and make my overall profile a little bit less complicated. And when I come down here, we'll do, one feature there, one here, and accept. And then I'm going to put one three-point arc over in this area. So just kind of working my way around the part until I've got the majority of what I need sketched. I'll do one more here. And you'll notice that the Auto Sketch command, when it could, already started applying constraints for us or relationships in certain cases. So the Auto Sketch command, if it finds one of the lines or that I sketched was close to horizontal or close to vertical, it went and assigned a vertical or horizontal constraint for me automatically. If it found a arc that was close to tangent to a line, or two arcs that were close to tangent to one another, it would apply a tangency constraint there as well. At this point, I've got the major features all sketched, but you'll notice a lot of green dots on the screen. These are kind of our accuracy analyzer disjoint ends checking function, which is a tool that I really, really like, and I wish that other software had an easier way of doing this to tell me that this profile that I'm sketching right now is not closed. And so for those of us that are used to doing, CAD sketching, the way that we close our sketches is a trim command. We have a corner trim tool just like SolidWorks does, and I can just find those green endpoints, find these very small features that I'm trying to extend here, and eventually get myself to the place where I have a fully closed profile. And actually, in this case, I believe this is more a vertical line here. So just a couple more seconds and I'll have a complete profile. And we'll go ahead and move on to the next step. Now, to Ian's point, certain fillets may not be appropriate to do in a sketch. It may be more appropriate to do that in a modeling operation in 3D. How you approach that is kind of up to you. I think usually it's set by a certain radius value. In this case, I do want to apply a fillet between two of these line features here, or actually a line and an arc, to get more of a a nice easy transition here for my revolve profile. And the fillet command in DesignX is kind of unique in that it's dynamic. I can actually assign a radius value to fit over my cross section just by holding the mouse button down and dragging that until it kind of fits that feature. Then it's going to build me a radius value there. And so if I want to control that radius value, just double click and get that to 30 millimeters, which is a nice whole number rather than 29.77 something or other. Same thing if I want to control the overall dimensions on this. We have the same smart dimension tool that SolidWorks has. So I can click two parallel lines. I can override my dimension here if I want this to be an exact 50 millimeters, and I can see how that changes the deviation that I'm going to get between this sketch and the cross section underneath. But at this point, this is a complete sketch. It's not a fully defined sketch, but it is at least a complete sketch that I can revolve. So I'll go ahead and exit out of my sketch command, and we'll go right into the solid body revolve command. If I show my meshes here, I know that I don't need to do a full 360-degree rotation, so I'll just make sure that I'm building this revolve a little bit bigger than the solid body or the mesh that I have there, and we'll eventually create some new features that will cut away the excess later on down the line. Now, I've built my first solid body from that area there, and I want to check to make sure that it is actually representative of what the scan data says it's supposed to be. Easiest way that we can do that is by borrowing a tool from our dimensional metrology or inspection software, the color map tool, and it basically compares the CAD model to the scan data, gives me a nice heat map telling me where my model is high and where my model is low. Right now, I've got it set up so that there's a 1/10 of a millimeter tolerance zone. So anything that's green is within plus or minus 0.1 millimeters. So about 0.004 of an inch. And for the most part, at least on the features that I have modeled, I'm seeing, pretty good conformance there. I am noticing that, in an area down here, which I believe to be actually a damaged area of the mesh, that is correct. There's some tool marks there. I am seeing some deviation there. So I'm not going to worry too much about the yellow and red colors here. As much as almost 0.5 millimeter in deviation down there towards some of the ugly areas. But I don't want to create those tool marks in my final product when I actually go and manufacture this thing. So I'm ignoring the scan data in that area and just kind of applying my own design intent to this model.
And we have one question.
So the
here.
next,
Someone wants
sure,
to know,
yeah.
When you change the dimension, I assume he means override a dimension, does it still continue to use the scan data, and what kind of best fit is it?
So it does not. We've removed our constraint to be fixed to the scan data, and we've overridden that dimension to move that feature. So I can go, if I go back into my sketch here, and this is an excellent question, by the way. If I want to, for example, control this dimension and say, no, 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 I want this tool to actually be 60 millimeters. Oh, yeah, not 600, 60. And it's going to modify the sketch. And of course, since it's not constrained, it's going to blow the thing up on me. But it's going to move that feature so far off of my cross-section guide there that there's clearly no best fit happening, or no fitting method, period, happening. The only fitting that happens is when I create the feature in the first place, but I have full control over that, and I can completely remove my sketch entity from the mesh if I so choose to do so. And I don't need to use the mesh for anything. If I want to make a new feature on this part, I still have all of the standard tools here. I'm not beholden to fitting anything to that cross-section guide whatsoever. But the cross-section guide is really just there to tell me this is the ballpark that I need to be in. This is roughly the shape that I need to be in. You have full editability beyond that, but here's where we go. And it's nice, it's a good idea to point out while I'm in this command, or I'm in the sketch mode here, that heat map that we had between the solid body and the mesh is also available between the cross-section sketch guide and the sketch itself in the form of the accuracy analyzer here. If I choose deviation and I zoom in on an area that I know I'm going to have some deviation in, like this, maybe since I didn't round this corner out, I can see a 2D whisker plot giving me an indication of how far the blue sketch elements that I've built are to the cross-section guide there. So it's really nice to know, even before I start to convert this into a 3D object, into a solid body, that the sketch that I'm generating is representative to whatever my design tolerance is to the scan data that's being used as a template. So yeah, excellent question. So now I'm out here. I have my first and largest chunk of the CAD Solid built. I'm going to hide that for a second, and I'm going to show the mesh, and we're going to go ahead and model our next feature here, which is this little extrusion that comes out of the side of it. So if I want to build a plane that is, just a rotation or an angle off of one of my system planes here, I have every right to do that. I have every ability to do that. If I want to be a little bit more quick, since we're, kind of in the interest of time here, and I want to let Matt do his thing throughout the, in a few more minutes here at least, and show you some more organic modeling. I'm going to do this the more quick method, where these regions that we've extracted here can basically be used as reference geometry without me creating and constraining reference geometry. So I can right click that region and I can place another mesh sketch on it. Now this isn't going to need that revolution or rotational style that we did before. So I'm just going to offset slightly into the part, making sure that I ignore this fillet. All scan data is going to inherently have some very small rounding on sharp corners. So as long as I offset into the part that way a little bit, I can get another cross-sectional guide here. And again, I can use either my auto sketch or my standard sketching tools to build this. Now, this is a very simple sketch, so I'll just click.
And another quick question here. Someone just asked,
yeah, of course,
what is the name of this software? So for anyone who missed it, this is Geomagic Design X. There are a few different Geomagic products, including a plugin for SolidWorks, but this is Geomagic Design X.
Perfect. So I've got that feature built. I'll go ahead and do an extrusion here. And I'm, of course, going to go into the part and make sure that I merge with it. But when I look at this and I think about it, well, I'm going to be not modeling some of this area down below here. And when I look at my CAD Solid, I've got a lot of excess down here. So again, since this is all history-based, what you're used to being able to do is just editing the sketch. We'll just drop this line so that I've got an excess of material, so that when I extrude through, I'll have plenty of material there. And now I can go to my Model tab. Model tab is just the standard solid and surface modeling commands that you're used to seeing inside of SolidWorks and other CAD systems. And of course, from here, I can use my front plane to cut my solid body with the top portion remaining. And now, minus all of these holes and these inserts for dowel pins and stuff like that, which I'll get to later on down the line, the lower portion of this model, at least, is now complete. I can check my deviation there. It looks good so far. I probably need to pull this line feature in a little bit, so I can always modify this again, make sure that I do have a good best fit on this line, which did not happen when I overrode this and put a horizontal constraint on it. But let it update. And we'll move on to the top now. The top's going to be a little bit more tricky because I've got, not only do I have 3 somewhat freeform organic surfaces up here, but they also intersect in very interesting ways. I've got these very small lips, one on the top here, and then one kind of inset corner on the bottom here. Now the top one's not a big deal. I can fit a plane to this. It's a basically linear surface, so I can fit a plane to that very simply, just by using what we call the primitives tool. And I'm going to save because it's always a good idea to save, especially when GoToMeeting or GoToWebinar is running in the background. But I'm going to select this region, this small region here, and I'm going to tell the software just to build me a surface plane from it. Oops, that's a cylinder. So what we'll do is we'll extract a surface plane from that. We'll also extend it because it's a very thin shape. I want to make sure that when I'm trimming this with some other surfaces, I'm going to have a much better ability to do that. So even when I'm using some of these automated tools like the surface primitive there, DesignX knows that this is supposed to remain a history-based model. So when it builds that feature, it actually builds me a sketching plane, it builds me a sketch, and it builds me a surface extrude, and all of this stuff is totally editable. If I want to either dimension this or change the angle of it, or even just resize it to make sure that it's going to interface with the other surfaces that I'm going to generate in a second here, I can do that. And of course, I can always check the deviation of that relative to the scan data that it's in. Now, of course, the thin center section here is the only deviation that we're worried about. And I've got green areas there, so I'm pretty happy with that. And we can move on to the next feature. Next feature up top here, I'm going to model the exact same way. The surface cylinder, very simple. Click it, click the cylinder option, and it's going to give me a preview and build that there.
All right, so now that we've got those 2 surfaces built, let's go ahead and take a look at these a little bit more organic shapes here. This region, when I hover over it, tells me it's a revolution. I could try and find an axis of revolution if I wanted to and make a sketch that would be appropriate there, but I could also just treat this as a organic surface. And one way that we can extract a single organic surface from a region of the scan data is by using the mesh fit command. Mesh fit command is very simple to use. I just select the region that I want. I can orient the surface to make it a little bit more in line with some of the other features on the model, and I can of course resize it to make sure that it's a little bit bigger than it needs to be so it can trim with other surfaces later on down the line. I can also change the complexity of this surface, and when we're doing basically any type of organic modeling inside of DesignX, there's always a balance between how complex the surface needs to be and how smooth and therefore potentially how manufacturable that surface should be. So this control net density will allow me to make this less complex with fewer control points being attached to the mesh and maybe potentially a little bit less accurate to the scan, or I can maximize that and get a more complex surface, but something that's also going to be a lot more accurate to the underlying scan data. While I'm in this preview mode, I can use my accuracy analyzer to tell me if the settings that I'm using are appropriate and if I'm maintaining that design tolerance. So if I go all the way down to the bottom here, I notice that I'm not really losing any accuracy to the scan data, and I am getting a lot less complexity from this surface. So I'll go ahead and accept that. And this is a surface that gets built as a mesh fit command inside of DesignX. If I need to edit this, I can do this here, but since SolidWorks and no other CAD package actually have a mesh fit command, when this data gets transferred into those downstream CAD systems, I'm not going to have the ability to edit it there. It's just going to show up as like an IGES surface that can still be used as a surface body, but not edited there. So definitely keep that in mind. If I do want to make edits to a freeform single surface here, we have another tool that makes it a little bit easier to do. This Loft Wizard command will treat this surface here as a series of sketches essentially that can be lofted between, and this is something that's a little bit more akin to the standard freeform modeling style approach in a history-based CAD package, where the sketches that this software or this tool rather build can be edited downstream. It's a lot easier to to edit these sketches if I choose to do the reference planes and mesh sketches option, where it'll create a cross-section sketch every time that needs to create a cross-section here. Or if I want to just keep my history tree a little bit more clean, I can use the 3D sketch option. I don't have quite as much editability to this. I still can make some changes to it, but maybe not quite as easily as I would be able to if it were 2D sketches. I can choose to do a cap the number of cross sections and therefore number of loft profiles to a certain number if I want to, or I can let the software just guess and create as many as it needs to adhere to a certain tolerance. In this case, I'm just going to keep this as simple as possible using 4 sections. And when I hit next stage here, it'll give me, again, a preview of the surface that it's going to generate. Now, by default, the software does want to try and keep this as smooth as possible. I think in my previous step, I had a smoothness slider that was pretty close to maximum. And the smoothness that I get here is going to basically limit the number of control points on all of these splines to 5. And if I use my accuracy analyzer to test the deviation that I'm going to get there, not exactly ideal. So maybe adding a little bit of complexity, maybe doing 10 points instead of 5 is going to give me more accuracy. Of course, if I did 15 or 20 points, I'd probably be able to get even more than that, but this is going to be enough for my purposes here. So we'll go ahead and let the software build that. Now this is going to build a sketch and a loft operation. So if I need to create guide curves, I can do that, and I can add those to this here. I can rearrange my history tree so that the guide curves would be above the loft operation. And I can edit that 3D sketch just with the standard 3D sketch editing tools that we have access to. I can smooth these, I can elongate these splines, I can remove points if I need to, or I can add points if I need to. So some amount of editability there, definitely going to get more of that if you have those mesh sketches in the 2D cross-section planes. But basically 2 different ways of creating freeform surfaces from a region on the mesh. Now the last thing that I need to do here, this is going to be the trickiest thing to model. So that's going to be this little channel here. And the reason that it's tricky is it's not really on a straight profile. So doing the same operation that we did above here where we had that plane built, not going to work unfortunately on this section here. So what I'm going to do is I'm going to access a new tool here on my 3D sketch tab. This is a different way of using the mesh as a reference object. Instead of taking a cross section, I can actually throw splines directly onto the triangles here. I can do that manually. I can just kind of click the points along this curve that I need to, or I can introduce a new cool tool here called Trace Feature Line, and that's actually not available in 3D Mesh Sketch or 3D Sketch. It's available in 3D Mesh Sketch. So this enables me to be putting all of my spline points directly onto the scan data. That Trace Feature Line will basically allow me to come in here and similar to how we did the extract regions tool where the curvature of the mesh broke up the scan data into different regions, I can use similar kind of algorithms to chase this sharp corner around the part. So it'll continue to chase that as it sees any of those mesh areas that kind of conform to that 90-degree corner. And of course, I don't need all of that, so I can tell the software just to isolate this section of interest here. And so it's going to build me a 3D spline. Every one of those spline points is going to be located on the mesh. So the first thing that I'm going to do here is use that spline to create a plane perpendicular to it, because I'm going to basically create a sweep of a profile along this 3D spline path and use that to kind of trim this loft wizard surface with this mesh fit surface here. So with the add plane tool, I can use the end division option. I can select that 3D sketch, and I can choose to offset, or I can basically put planes perpendicular to that at multiple locations along that curve. So now I can find that plane that I just built. And I can, first of all, since I'm going to be creating a sweep profile, I need to make sure that the sweep and the path do connect with one another. So I'm just going to make my life a little bit easier and create an intersection point with that plane and that curve, and then create a mesh sketch on that plane. In this case, all I really need is just this little linear section here. So this is a lot of detail work just to get this thing right, but it's very simple once you have a good approach kind of dictated in your head. So I'm going to, like I would inside of SolidWorks or other CAD, use my Convert Entities tool to convert that point of intersection, and then I can hide that sketch. And then I'm going to use my Line tool to fit a line to this section of the scan data. And just like in normal CAD, I can create a common constraint between those two that is a coincidence constraint, and I'm just going to resize this line so it's a little bit longer and definitely will protrude through both of these surfaces that it's intending to trim. So from here, we'll go ahead and find on our Model tab the Surface Sweep command. That profile is already selected. The path is going to be this guy, and maybe I want to, if I were being a little bit more detail oriented here, if I wasn't operating with some time constraints, I'd probably come in and try and smooth this curve a little bit just to make it a little bit more, get some of this wiggle out. But essentially, I do want to just let that build. So that's going to sweep a surface here and generate that last piece of the puzzle so that I can trim all of these bodies or these surface bodies together and then use them to cut away the solid. I'm going to do this in a couple of steps. The surface trimming tool inside of DesignX is very similar to that inside of SolidWorks, but since I've got some very small gaps to deal with here just to kind of keep my head straight, it's going to be a little bit easier if I just do multiple trims rather than trying to do them all at once. So trim surface, I'll do these guys together, keeping that and this first of all. And I actually probably should roll back here and just extend a couple of these guys because I know that they're not going to extend all the way through this solid, and that's going to be really helpful. And it's actually easier to do this extension while there's still individual surfaces here. So I'll just grab that, make sure that they are big enough. Do the same thing with this, and I think everything else is going to be fine in this case. Everything should be extending through. We'll find out one way or the other when we do a cut in a couple of steps here. So I'll go ahead and roll forward through and just let that surface trim build again. And I think I actually chose the wrong things to keep. So let's keep the lower half here. There we go. And then do another surface trim between these guys, keeping that, and this. And one final one between these two bodies. Okay, so that should be, again, protruding all the way through this solid body and can be used to cut it. So I'll choose that as my tool, solid as my target, keeping the lower half here, and voila, there we have it. That top section has been modeled. Now it's really just up a case of, adding some details here. Like I know that I'm going to have some deviation in these areas because I've got some fillets there that I need to model. Very simple to do that. Actually, really, really nice to have a mesh as a guide in this case because I can choose to fillet that edge, and actually I'll choose these two as well. And I'll let the software estimate the radius of the fillet from the scan data. So essentially along that edge path there, it'll cross-section the scan data in a number of places and average out what it finds to be the fillet radius when I use this estimate command. It's going to tell me somewhere in the range of 1.3379 millimeters, and I know that that's not really a real number. It's probably not going to be the number that we want to use. I can always change that to 1.25 or maybe 1.5 or whatever fractional version of millimeters I want to use, and assign it that way. And of course, I can always check my deviation too with the accuracy analyzer at every step of the way. Do the same thing over here. I know that this fillet's going to have to add a couple of these little profiles as well. And again, we'll estimate it. Maybe we'll use the same radius, maybe it won't, but we don't have to kind of manually go through everything. Okay, yeah, 1 1/4 seems to be about right for this. And from there, all we really have left are some of these, dowel pin cutouts. And I'm not going to model every single one of them because the process is roughly the same. I can manually sketch some of these things, but I do want to show just some other kind of automated modeling tools, if I may. So something like the Revolve Wizard, which is actually on the wizard commands here, Revolution Wizard. This is another kind of automated tool that if I select a couple of these features here, actually I need to tell the software that I want to use those features to define a sketch and a revolution operation that cut away from my solid body. I can choose solid cut, hit next stage, and the software will give me a preview of the depth of the cut. It'll even add this chamfer, which is in the form of a sketch chamfer right now, which may or may not be the most appropriate, but I can hit OK, show my solid body, and yeah, I should probably go in and actually chamfer that rather than letting the software do it as part of the sketch. But I can do that really easily here. This is a sketch that the software created. Oops. Do this guy, and I'll just remove that kind of that angled feature there. Finish this sketch. It's just a basic cylinder, and it still does a cut operation, and now I can use my chamfer tool. Chamfer tool has the same searching function for the dimensions of that chamfer. So if I want to edit this and make it 0.4 and 45 degrees, certainly have override capability there. But that basically does it. I'll just kind of finish the process by doing the same thing on these remaining features here. And at this point, the model is, we'll call it done. And I can export this, right click, export as standard file formats, IGES, step, parasolid, binary or text, ASICs. And we can even export CATIA.model or .catpart v4 or v5 files. These will be basically just dumb solid bodies, though. I'm not going to have any of this design history. And, to be honest with you, most people that have DesignX spend the majority of their time inside of SolidWorks. This is something that they use maybe usually once a week or so, but they're using SolidWorks once a day. And so they're more familiar with SolidWorks. So at this point, if they want to make any edits, add constraints or dimensions, or do an assembly or do a drawing or anything that you would use SolidWorks for in general, this solid body is now compatible with SolidWorks.
And we've got an entire history tree here that we want to transfer over. Of course, I can right-click this, export as just a standard IGES step, parasolid, ASIS file, and even go into a CATIA V4, V5 model or cat part. Or if I want to actually do something that's not a dumb solid, I can choose the SolidWorks live transfer command, which will open up SolidWorks in the background and start to rebuild all of those sketches and modeling operations and constraints and dimensions and everything inside of SolidWorks. So this is all totally hands-off at this point. It takes a few minutes to do this live transfer, so I'll just basically let it kind of build here, but I'll show you what it looks like once we've already completed the process, and all of this modeling history here can be interacted with inside of the SolidWorks or inside of SolidWorks. This can be saved as a native solid part file now, and I can even edit all of the sketches that make up all of the features on this model here. If I can find this guy. Way too big. So I can edit dimensions. I can change the location of things. This is a native part file at this point. Matt, with that, I'd like to turn it over to you, my friend.
Thank you.
Awesome. Thanks, John.
Yeah, thank you so much for showing the prismatic side of it, more surface modeling. So what I wanted to discuss in my section was more on the hybrid, so an introduction into the hybrid. A lot of times when we work with modeling, I have a slide up here just showing two examples where we'll have something that's pretty prismatic, but then we have those surfaces that we do have to use mesh fit on because it is going to be impossible to model with a series of spline lines. Or we have something on the vice versa, or we have something that was actually manufactured with topology in mind or 3D printed, like this bracket on the bottom left of my screen. And it's something that, it's very freeform, but we have these sections that we need to make sure are prismatic. It was hand carved, for example, but we have bolt hole positions that we need to make sure are, the dimensional size, the proper fittings. So we do something called hybrid modeling. And hybrid modeling really is the idea that bridges the organic freehand sculpted side of modeling with the prismatic side that we were showing earlier. So we're able to do examples, like I said, the top left, where we have this demo block and we only have 2 or 3 faces that were maybe fitted in to connect with the tooling, but everything else is pretty prismatic. Or again, we have the bottom left where everything is freeform, but we have these sharp corners. So DesignX has ways to use that mesh fit to combine everything together. But on top of that, there's something in DesignX called auto surfacing. And auto surfacing allows us to do something like this, where we have something that is just truly freeform, truly handmade, like the statue top that we need to reproduce as a solid. So if we need to remanufacture it, or we need to combine it with a designed base. So in this scenario, I've done something called auto surfacing on the statue. I've designed my base up, and then because they're both solid bodies now, I can now have them interact with one another. I can, CNC this, and I even added in the fountainheads, which were also hand carved using series of surfaces. So I extracted a couple surfaces from that. I'm able to use something called like a solidify tool in DesignX to combine everything together. So this is the idea behind hybrid modeling, and I wanted to just show a brief little example of this. So how we can apply it inside of the workspace. So here we go. We have our example file up here. This is that block, and I'm going to use something very similar that we just saw a moment ago, that mesh fit. So on our solid block, if I hide my mesh, as you can see, I have this flat face, but this isn't the way that it was created inside of our actual manufacturing. We have this kind of bump right here, and as you can see, DesignX recognizes it is a freeform shape. So this is something, again, that might have interacted with the tooling, but we need to make sure it's exact. We can't just estimate and just assume that it's going to be used or manufactured that way. The CNC will not know that, or the mill won't know. So what I'm going to use is that mesh fit surface, and I'm going to select on the region. And I'm going to, again, show that little preview of the mesh fit just to make sure things are exact how we want. I'm going to increase the density maybe just a little bit. But the idea here is that I am taking something that's pretty prismatic, straight lines and flat surfaces, but I'm adding on top something that I do want to be freeform. Well, this is great. I have this surface. If I do my deviation analysis, you can see it's pretty good. I have, little spots here and there that I can improve upon, but that could just be a nick in the machining. But how do I actually now get this to work with my solid? As you saw, it's actually extended out. So unlike what Sean showed, what we're taking away, we need to now add this freeform shape. Well, we can do something inside of DesignX called the replace face. So this is very similar to SolidWorks. We have the little command right here in this corner. I can select on that. I can say the faces that I want to replace, and I can say the surface that I wanted to replace with. So just 2 simple commands. I'm now able to insert in or replace my face with this freeform surface. And if I hide that surface, I now have this hybrid combination. So it's pretty quick and easy. I can do my deviation analysis. I can see that it is true that it took that surface and is using that. So again, this is the idea behind hybrid modeling, being able to just take sections that we just normally would not be able to model and just quickly replacing it with mesh fitted surfaces that we can. So I want to show another little example. So just like I showed it, that block, I'm now going to just show the bracket and how that auto surface works, because I just showed it initially, it looks like it was a bunch of lines and, I got a solid, but what actually was happening in the background? This is something we're going to go a little bit more in depth with in the next month's webinar, that freeform, how to model everything part 2, where we're truly working with organic shapes. But in this scenario, I want to turn this into a solid body, so at least I can start working with it. It's actually going to be pretty easy to do. I've copied over my mesh, so this is my copied version, and I'm going to manipulate this in getting rid of all these holes, because these are the sections we want to replace with our fitted areas. So DesignX, we have ways to manipulate our mesh. I'm in the Polygons tab. I'm going to just hide, or I'm going to select all these circles. Just holding down Shift and selecting multiple areas. And I'm just going to delete these. So direct editing onto the mesh, and then just using a hole fill to fill everything back up. Because I want this to be watertight when using the auto surface tool. I also want to make sure that it is properly healed up and we don't have something called non-manifold sections. Essentially, non-manifold sections are where surfaces or meshes, parts of it blend together, something that we don't really want when we're trying to get an exact one-to-one mesh. So if I just click confirm, everything looks pretty good. It's going to try and heal up all the sharp corners. And here we have it, our watertight healed mesh. And now I can go over to the model tab. Oops, sorry, I can go into the home tab. We have auto surface. So auto surface, again, I want to take what is here and turn it into a solid body. I'm taking areas that I know I would never be able to model and just turning into a solid so I can add in my cuts. So I'm selecting that this is an organic shape. I can adjust my geometry accuracy if I want that. But for now, I'm just going to click next stage. And what this next stage is going to do is going to build up the NURB surfaces that define our auto surface. So what are NURB surfaces? Well, previously we were using spline lines to create that loft surface. And that's essentially what's going on here. We're creating a series of spline lines that are going to go all around our mesh. And that's what's going to create our one-to-one. And with all these spline lines, they're going to be broken up into smaller sections, just like here, where we have different blocked spots. Essentially, all these are just the mesh surface, or the surfaces are going to be made using these spline lines. Everything looks good. It looks like it healed up pretty well. So I'm going to click OK to confirm this. And it's now just going to go through and just complete the process where it's taking all the spline lines, creating surfaces from them, and then stitching them together. And again, all these mini surfaces, those are what I was referring to as the NURB surfaces. And once this completes, we're going to have our complete solid body. So as I said, we now have something that we can machine with, and we have something that we can start doing actual modeling off of. So just completed, we have one solid body in our feature tree. And just to add in that little circle, I'm going to just use this top plane right here that goes right down the middle. I'm going to use that mesh sketch tool. And with this, I'm actually just going to use it to extract, need a mesh to show. I'm going to use it to extract what the centroid of this part is. So being able to just use some sketch lines right on top of it, going to define what that circle center is. So now I have something that matches that exact circle, that part of the bracket. Adding in an extra little hole, cut, sketch, maybe adding in a dimension, completely prismatic and modelable now. And with this, I'm just going to extrude it out as a cut, both directions, and in the end, we have our bracket. So something that we use the auto surface to turn into a one-to-one, getting all the parts that we don't want to model, but we know we need it as a solid, bring it into a solid, and then adding in our actual features afterwards, this hybrid modeling. We did that very similarly with that demo block file where it was something that we already had pretty much modeled, but we had this one surface area that we needed to be hand carved. We're able to turn that into a mesh, that mesh into a surface, and then apply it to our solid body. So this is just a brief little introduction into the idea of hybrid modeling, but as you can see, it applies a lot of the same rules that Sean was just showing, which is using some extra surfacing tools and the ability to just take one-to-one references from the mesh. So that was just my section I wanted to go over. I'm going to bring it back over to Ian, who can add some extra closing statements.
Awesome. Thanks, Matt. We want to help you. We want to hear from you. So let me know how we can help. And thanks, everyone, very much for joining today.